Hi, my name is André Costa, and in this presentation, I'll talk about a new approach for the simulation of hydraulic fracture, which we call the multi-resolution method. This work was done in a collaboration with my colleagues at the Lawrence Livermore National Lab and Ottawa University. First of all, I would like to introduce the concept of a hydraulic fracture and its enormous importance in the field of geomechanics. Hydraulic fractures are simply fractures that are filled with a fluid whose pressure leads to crack propagation. They are very common in many geomechanics applications, such as oil and gas extraction, induced seismicity, carbon storage, and enhanced geothermal systems. Therefore, a lot of research has been pointed towards the development of numerical methods that can accurately simulate this phenomenon. Most of the computational approaches for hydraulic fracture simulation can be separated in two classes. The first consists of approaches where the cracks are introduced as actual surfaces in the domain. We call these the sharp crack approaches, and their strength lies in their ability to represent discontinuous displacement fields from which the aperture, which is very important in hydraulic fracture, can be computed. Another advantage is that these approaches tend to be computationally efficient in terms of the discretization density needed to compute an accurate solution, especially when compared to the next approach. The disadvantages, though, is that one must rely in some type of post-processing criteria to evaluate whether a crack will propagate in a certain condition, as well as the direction of this propagation. Especially when working in 3D, or in the case of crack emerging or branching, this can become very cumbersome. The second approach involves the regularized methods, including damage mechanics and the phase field method. In these, the cracks are smeared over a volume and there is no clear crack surface. Specifically for hydraulic fracture, this is a considerable drawback because additional modeling has to be done to extract the aperture. The mesh resolutions also need to be very fine to resolve the regularization length, making these approaches computationally intensive. However, they have a great advantage, which is the incorporation of the propagation phenomena in the governing equations, removing any need for remeshing, post-processing, etc. Branching, merging, and complex curving in 3D can all be easily handled by the solution of a PDE. In order to combine the advantages of both these methods, some attempts towards hybrid models have been made in recent years, but none has looked into hydraulic fracture problems. In Giovanardi et al., the phase field method is applied in a small subdomain in the crack tip regions, effectively acting as a crack propagation criteria for an underlying XFEM representation of the fracture in the whole domain. In Gillen et al., the authors developed a coupled XFEM phase field method using an optimization strategy to identify the crack surface, where XFEM enrichments are added. More recently, Mushi et al. Used the Nietzsche method to couple a phase field problem in a crack tip domain with an XFEM problem on the rest. The approach that we present today, which we recently submitted to the International Journal of Fracture, extends the idea of a hybrid approach to hydraulic fracture. It uses the phase field method in subdomains around the crack tip, similarly to the work of Giovanardi et al., but for improved accuracy, in the cases of rapid crack propagation, we also add additional global local iterations. This new approach allows us to use the phase field model as a propagation tool in hydraulic fracture, facilitating the computation of the fracture's geometric evolution without resorting to crack apertures modeled from a smeared representation. Its design also makes it very simple to incorporate in existing hydraulic fracture solvers. In a nutshell, our approach works in the following way. The cracked domain is discretized and the fracture is treated with a sharp crack approach. We call this the global discretization. Near the crack tips, subdomains are constructed and local meshes are generated, and in these, the phase field method is used to represent the cracks. These domains overlap with the global mesh as shown in the picture. We then solve the global problem, assuming that the crack geometry is fixed. With the obtained solution, we then launch in the local problem by passing the displacement field as a boundary condition and the pressure as static body forces. Importantly, we do not solve for pressure in the local domain. The solution computed with the phase field in the local domain then informs the global domain about crack extension. These global to local iterations are repeated until an equilibrium configuration is reached. Here we have a better depiction of the algorithm, showing how the iterations between the global and local solvers are performed and how we advance in time only after an equilibrium state is found. These iterations allows us to accurately compute the crack speeds and even converge in situations where unstable cracking is observed. We will now go over more detail about how we solve the global and local problems. But first, it is important to emphasize that this algorithm is completely agnostic with respect to the numerical methods. If one wants to use a different sharp crack representation or a different flow solver or even a different formulation for phase field fracture, this framework can still be used in the exact same way. First, to represent the cracks in our global domain, we employ the embedded finite element method, which consists of an enrichment strategy that allows us to represent displacement jumps over arbitrarily oriented line segments embedded in our mesh. These enrichments are done at the element level, and the segments must start and end at element edges. This local character of the enrichment strategy allows us to statically condense the discontinuous degrees of freedom at the element level, reducing the overall computational cost and improving the condition of the linear systems. For more details, we recommend the works by Linder and Armero, Borja, and Cusini et al. Oh, and it's also important to mention that these line segments are also used as 1D finite volumes for the computation of the fluid flow solution in a fully coupled manner. Here we have the governing equations for our system. In the global domain, we use the standard mass and momentum balance equations for the matrix and for the fracture. The constitutive choices are simply those from linear poroelasticity in the matrix and lubrication theory for the fluid flow within the fractures. It's important to mention that we use finite elements to solve the momentum balance equations and finite volumes to solve the mass balance equations. In the local domain, we use the phase field formulation for pressurized fractures in a poroelastic matrix presented in the work of Yoshioka et al. It is a variation of formulation obtained by minimizing this energy functional that depends on the displacements, phase field, a matrix pressure field, and a fracture pressure. These can be solved with standard finite elements. The pressure fields are assumed to be fixed as they are transferred from the global problem. This allows us to remove the need of extracting apertures from the phase field cracks that arise when one tries to couple the phase field and the flow solvers. Two important details of this algorithm that will depend on the numerical methods used in the global and local problems are the transfer of pressures from the global to local and the crack propagation scheme. Let's now present how it's done in our case. For the pressure transfer, we perform two different operations. First, for the fracture pressure, since the phase field formulations requires it to be defined in the entire local domain, we construct this operator pi f, which for each point of the local domain searches for the closest fracture cell in the global domain and gets its pressure value. For the matrix pressure, we could simply get the value at each point from the global domain, but we actually choose to apply a smoothing operator in an attempt to regularize the pressure field, which in the global domain is much coarser and constant over cells because of the finite volume scheme. This smoothing operator simply takes an average of the matrix pressure in the neighboring cells of a local element. This average uses the distance from the local element to these cells as weights, as shown in the picture. For the propagation scheme, we track three geometric entities and their relative positions tell us how to propagate the discrete crack. On the global domain, we track the position of the crack tip and the tip element, which is the element right in front of the crack tip as shown in the figure on the left. In the local domain, we track the phase field crack tip. While this local tip is inside the global tip element, we simply don't have the resolution to modify our global crack geometry. However, as soon as it moves outside of it, we can do a propagation update as described in the figure on the right. The identification of the phase field tip is still a challenge. We do it by looking at the phase field values in the nodes that are farthest from the crack mount. But more robust schemes are being investigated. Now, let's look at some example problems that we use to verify the accuracy of our approach. We start by looking at the well-known KGD problem. It consists of a linear elastic, impermeable solid with a crack where a viscous fluid is injected at a constant flow rate. The geometry and model setup are shown in the figures on the right. This problem has two asymptotic regimes for which an analytical solution can be derived. We solved it in both of these regimes to check how well our method compares to these analytical solutions. In the toughness-dominated regime, where the viscous effects are negligible and the pressure distribution is almost constant over the fracture, we are able to convert to the analytical solution as we refine our phase field regularization length. This verifies the accuracy of the crack propagation criteria based on the phase field solution, as long as the regularization length is sufficiently small. In the viscosity-dominated regime, the pressure distribution within the crack is not constant and actually has a singularity near the crack tip. The fracture toughness is negligible in this case, and all the energy is dissipated by the viscous forces. We found this case to be less sensitive on the phase field regularization length and more sensitive on the time step size. By refining the time step size, we were able to converge to a solution that is very close to the analytical one. However, due to the creation of new fluid cells with non-zero volume as the crack propagates, our computed pressure was about 5% below the analytical solution. This is a known issue with standard finite volume solvers for hydraulic fracture and will be addressed in future work. We also considered a case where the matrix is poroelastic, saturated with a viscous fluid, which is injected with a constant flow rate, as in the previous problems. In this case, we could not find an analytical solution, so we compared our results to the phase field model by Mihi et al. Their model treats the pressure loads in a different way, And throughout the development of this work, we found it to be less accurate when solving the KGD problems. However, to make a fair comparison, we modified our phase field equations by removing the pressure driving force in the evolution of the damage in order to match their model. By doing this, we are able to have a good agreement with their results in this problem. For reference, we also plotted the results using our original formulation, which ended up being much different due to the differences in the governing equations. Finally, we looked at a case where the crack trajectory is not straight. To do that, we consider this modification of the KGD problem where we add a circular inclusion in front of the initial crack. This inclusion has a larger Young's modulus than the surrounding rock. Qualitatively, we expect that larger ratios between the inclusions and the matrix's Young's modulus will lead to more deflection in the crack trajectory. For a very stiff inclusion, it is likely that the crack will go around it almost in a circular motion. And this is precisely what we found. For an inclusion that is only 2 times stiffer than the matrix, we found no change in the crack trajectory. By increasing the inclusion stiffness, we started to see a deflection. Initially, the crack still cuts through the inclusion, but as the stiffness increases, it eventually takes a path that completely avoids it. These results agree perfectly with the expected behavior for this problem and highlight how the multi-resolution approach facilitates the propagation of cracks in arbitrary directions. But there is still much work to be done. Currently, we are trying to implement it with arbitrary meshes in 3D within the high-performance geomechanics code GeoSax developed at the Lawrence Livermore National Lab. Currently, we only have it working with 2D uniform meshes. In the future, we also plan to extend this framework to couple additional physics, multi-phase flow, and heterogeneous materials in order to simulate realistic hydraulic fracture problems which involve all of these. To wrap up, I would like to acknowledge the support of the US Department of Energy and the Hexascale Computing Project for funding this work. And this is the list of references for anyone that is interested in learning more about this topic.